So in this video we're going to take a look at the dependence of simple harmonic motion on time. We're going to do that in two ways, one through formula and then also through the graphical interpretation. We have already looked at some graphical interpretations. We so far have looked at the dependence between the acceleration as a function of the displacement of the simple harmonic oscillator. We also examined the force as a function of the displacement of the simple harmonic oscillator when we talked about the spring. And what we want to do now is to bring time into it. Now, that's not to say that we haven't talked about time, because obviously we have explored pretty deeply the idea of the period of the motion of the simple harmonic oscillator. But now what we're going to do is to look at the displacement as a function of time. We're also going to look at velocity as a function of time, and lastly we'll look at the acceleration as a function of time. Now normally what I would like to do is to show you the origin of this equation. I'm not really going to show you the origin of the equation, but we are going to sort of dissect this equation or deconstruct it so that you can see that it does match perfectly the motion of any simple harmonic oscillator. And in order to do that, what we're going to do is we're going to use the right side of the page to create the three graphs: the dt graph, the vt graph, and the at graph, to see how they relate to each other and how one is derived from the other. So we're going to start by drawing a vertical line that will represent the x-axis for each of our graphs. And for my piece of paper, I'm going to break it up into 2 centimeter sections. So we're going to have the dt graph, and every 2 centimeters I'm going to make a little mark and I'll show you in just a moment what those are going to represent. But I'm going to do that for each of the three. So now the VT graph, which will be directly underneath it, and every 2 centimeters, 4, 6, 8. I'll make my mark, and then lastly the acceleration time graph. And so if you need to, once I have the graphs drawn, to stop the video so that you can make a neatly, not just a hand-drawn graph, but one using a ruler, then you'll be able to take the time to do that. So on one axis we're going to have time. This will be the displacement, so that's positive and negative displacement. Then we have positive and negative velocity. And lastly, we'll have positive and negative acceleration. Okay, so if you need to, you should pause the video right now to go ahead and make that. Okay, so as I said, we won't derive the origin of this equation, but we do want to see that this does show the correct manner in which simple harmonic motion depends on time. So let's start by looking at the cosine function. The cosine has a maximum value of positive 1 and a minimum value of negative 1. When this portion, the cosine of omega t, which will never be a value more than 1, never be a value less than negative 1, is multiplied by the amplitude, then you can see we're going to get values for the displacement which will be on the high end, the positive amplitude, and at the lowest possible end, the negative amplitude. So at least in terms of the range of the possible x's that this equation can generate, this is going to produce a valid motion, a valid location or displacement for the simple harmonic oscillator. Now in terms of the argument inside of here, remember that omega is the angular frequency, and at some point this number inside of here will reach 2 pi, and at 2 pi the cosine function will return to its origin wherever it started. If it started, in this case, just a simple cosine function, if it started at its positive value of positive 1, positive maximum value, then at some point when this argument inside of here reaches 2 pi, then we will have gone through one full cycle. And let me remind you that, let's go back and look at the equations that we've generated. Notice that if I were to, for example, solve this equation, omega times the period, that would be equal to 2 pi. So at some time in the motion of the simple harmonic oscillator, when little t, the random arbitrary time, is equal to the period, then omega times that period of time is going to be 2 pi, and at that point the simple harmonic oscillator will have gone through one full cycle and will now begin to start the second full cycle. And every time it is a multiple of 2 pi, which you can imagine that if instead of being t, this was 2 times t or 3 times t or 4 times t, that every time that occurs, omega times that quantity, it will be some multiple of 2 pi. One multiple or two multiples or three multiples. This will be counting the number of cycles through which the oscillator has gone. So let's take a look at how the cosine function looks. So the cosine starts at its maximum positive value. It looks almost identical to the sine function, but starts at a different location. So I'm just going to turn this to make it a little bit easier for me to draw. And we'll assume that our maximum positive amplitude is here, and our maximum negative amplitude is about here. Okay, so at time equals 0, the simple harmonic oscillator would start at its maximum value, and at a point which is 1/4 of the way through its motion, it will have come to the point where it's reached its equilibrium position. Now, what's going to happen with the curve, just to remind you, that the displacement time graph also has other ways of interpreting. So, for example, we could look at the slope of this graph, and the slope of this graph, the position time graph, would give us the velocity. So you'll notice what happens with the slope is that initially the simple harmonic oscillator, which has been pulled out to its maximum displacement, is released with no velocity. But what happens is that it quickly begins to pick up velocity, and what's the direction of that velocity? The direction of that velocity is in the negative direction. And at the point where we pass the equilibrium point, this is where our velocity will be at its greatest, therefore the slope of this line will be at its greatest. And what's going to happen as it passes through that point? Well, ultimately we're trying to reach this point down here where we have the maximum negative displacement. So what's going to happen is it's going to begin to curve in the opposite direction until reaching 0 velocity, where again the slope of this line has now reached 0. The slope of the displacement time graph is the velocity. Now this is when it's reached its equilibrium, or it reached its amplitude on the opposite side. What's going to happen when it gets there? It will come to a stop and then begin to accelerate backwards in the opposite direction, picking up speed, going faster and faster until once again it reaches the equilibrium position. Realize this is 0, the equilibrium position, and at that point it will have reached its maximum velocity in the positive direction. So coming from the negative side, it will be moving towards the positive side, and at that point it will reach its maximum velocity. Therefore the slope of the line will be the steepest, and then it will overshoot the equilibrium position, and we want to return back to our maximum amplitude. So we'll start off with a very steep and return back. Okay, so this is the just simple cosine function. It perfectly describes the motion of the simple harmonic oscillator, and obviously we would be looking at a point here where this would represent the amplitude, the maximum amplitude in the negative direction, and of course on this side we have the maximum possible amplitude. How much time would go by? Well, when you multiply omega times t, this portion of the argument inside the parentheses, at this point that will be equal to pi over 2. Down here will be equal to, pi. It's an interesting way of making pi. Okay, so pi over 2. At the point where we reach the opposite amplitude on the negative side, that's going to occur at pi. Omega times half the period will be equal to pi, will always be equal to pi. Then we will have 3 pi over 2, and then lastly we'll have 2 pi, and we will have made it through one full cycle of its motion. Okay, so just to give you an actual concrete example of how this would look, Let me give you a specific version of this equation just as an example. So let's say that x is equal to 3 cosine of pi times t. So we're going to assume that in this case that omega has a value that's exactly equal to pi, 3.14, and that the amplitude has a value that is, this could be 3 meters or 3 centimeters or 3 millimeters. It has, the units can be whatever you want the units to be. And in that case the displacement will then come out in the same units. So let's assume for this one it's centimeters, for example. Then in terms of determining the period of this thing's motion, t is equal to 2 pi over omega. That would be 2 pi over pi. Those would cancel. And the period of this oscillator would be 2 seconds. And obviously with this period, then I could go on to figure out the frequency and so on. So typically when you look at this graph, you're not going to see pi over 2, pi, 3 pi over 2, 2 pi. These are not going to be the values on the graph. The values on the graph are going to be 1, 2, 3, 4, 5, 6, 7, and we might count by 10, 10, 20, 30, 40. But this is going to be a time in seconds. So it would be very unusual that a graph of time in seconds would be measured using multiples of pi or fractions of pi. So just bear in mind that, for example, this marker right here, this would say 2.0 seconds. This marker right here would say 1.0 seconds. Okay? So let's see how that looks when we take that to the velocity time graph. So on the velocity time graph, we're going to see a almost identical shape to it, but it's going to be shifted a little bit. So sine and cosine look exactly the same. So at this point where I release my simple harmonic oscillator, it starts with a velocity of 0 because the slope is 0. And what ultimately ends up happening is that we end up increasing the velocity but in the negative direction. So that means that instead of going up like you might think of the traditional sine function like this, we're actually going to go down, and we're going to reach our maximum negative velocity at 1/4 of the period, or pi over 2. And that point we reach the maximum velocity because I can see the slope of this is at its steepest in the negative direction. Then it starts to curve back in the opposite direction. So what's happening to the velocity of the thing is that it's slowing down. So imagine that you have the oscillator, you pull it out, you let it go, and then it moves back, picking up speed until it reaches the equilibrium position. Then it overshoots and then comes to a stop on the other side, and then starts to move backward, reaching its maximum velocity in the positive direction until finally it arrives back over at the original place where it started. So what's going to happen is we'll reach our maximum negative velocity, but then we'll come back not to the origin, not to the equilibrium. We'll come back to the point where the velocity is 0. The point where the velocity will be 0 is on the other side from where you started, again at the maximum amplitude. I mean, take a look. We will reach 0 velocity at the point where the amplitude is at its maximum. It is swung all the way over the other side, come to a stop, and now turns around and starts to head back, reaching its maximum positive velocity, which we'll say is about here, lined up with 3/4 of the way through one full cycle, and then returning back to 0, at which point the thing will continue to move in this exact same manner. So I'm just going to turn the paper for a second so that I can draw this. So we start off with no velocity, but quickly pick up velocity, reaching our maximum negative velocity. Then that velocity begins to decrease, reaching 0. Okay, so our maximum velocity, and for the purposes of this course, it is actually shown in the Soko's book, the derivation of these equations. It involves calculus, and for our purposes I don't really feel like it's that important. You basically need to memorize the formula that the maximum velocity will be omega A that is. Now, to point out, once again, this is the time axis. The period of motion of the velocity is exactly the same as the period of motion for the displacement, because it's moving through the same cycle. So the angular frequency here is exactly the same whether it be the displacement or the velocity, and we'll find the same thing when we go to the acceleration graph. So remember, for the displacement time graph, the slope was the velocity. For the velocity time graph, the slope is the acceleration. So if you notice, where is the acceleration the steepest? Right here. Now that should make sense, because there's a direct relationship between the acceleration of the object, and look here, very steep acceleration, very steep slope of the VT graph, and the displacement. So look, where the displacement is very high, we have a very large acceleration. But notice that this is a positive displacement and this is a negative acceleration, exactly as the formula that you've learned. A is equal to minus omega squared times x. So where we have a large positive displacement, I expect to see a large negative acceleration. Where I see a large negative displacement, I would expect to see a very large positive acceleration. So the graphs match up with each other perfectly. It follows the basic principle of simple harmonic motion, that A is equal to minus omega squared times x, or times the displacement. And the two graphs are going to move in phase with each other like that. Now they are shifted a little bit from each other. As if you notice, where the maximum negative appears about pi over 2 out of phase with the displacement time graph, and we'll see a similar thing occur down with the next graph. So here A is at its max, here A is equal to 0, here A again reaches its max, and here A is equal to 0, and then we're again back to A is equal to its max. And while we're at it, we'll go ahead and fill that in over here also. Remember, here V was equal to 0, V equaled its max, V equaled 0 again, V equaled its max, and V equaled 0 here. Okay, so by recognizing how the slope of this graph relates to the acceleration, then we should be able to translate that into our acceleration time graph. But it's actually even easier than that. We really don't even need to look at the velocity time graph, because let me remind you that the basic principle of simple harmonic motion, a formula that you absolutely should have memorized at this point, is that the acceleration is directly proportional to, but opposite to, the displacement, and there's a constant of proportionality, which is omega squared. If you remember that x is a cosine omega t. So that's where we get this equation from, right? Here's the minus omega squared from the simple harmonic motion equation, and x is equal to a cosine omega t, just as it was right up here. So we really don't even need the to translate from velocity to acceleration graph, but we'll kind of try to do both at the same time. So remember that A is at its maximum, but realize that A is at its negative maximum. So this is important to remember, that the acceleration is always in the opposite direction as the displacement. So here, where the acceleration is at its maximum, because the slope of this line is its maximum negative value, that occurred back where the displacement was at its maximum positive value. So when we come down to this graph, we're trying to line these three graphs up, realize that the acceleration will be at its maximum value, except that it will be at its maximum negative value. Right, and what will ultimately happen is that as the simple harmonic oscillator reaches equilibrium, this is the place where, for example, if we were talking about a spring, where the spring would no longer be stretched. So therefore there would be no force acting on the oscillator, the object, and therefore there would be no acceleration of the object. So the acceleration, I should say, decreases as we get closer and closer to the equilibrium position. Why does the simple harmonic oscillator keep moving if there's no acceleration? Because it has velocity at that point, considerable amount of velocity, and it overshoots the equilibrium point, causing the spring to be stretched on the opposite side. So we're going to go from our maximum negative acceleration up to a zero acceleration. That will occur when the oscillator is at equilibrium, at the equilibrium position, and then it will overshoot that position, reaching its maximum positive acceleration on the other side. So where the displacement is at its maximum negative value, we will expect to see the oscillator at its maximum positive acceleration. It will then return to 0, and then one full cycle later we'll be back to our negative displacement about here. Okay, so this is going to look something like this. Okay, not especially well drawn, but still we have the acceleration at its maximum negative value. It reaches 0, goes back over to the positive maximum acceleration. This would be at the maximum negative displacement, and then returns back to 0 acceleration. That occurs every time we pass through the equilibrium position, which on the displacement time graph is the axis of the graph. And then maximum negative acceleration every time we reach a maximum positive acceleration here. What's the amplitude of this equal to? Again, we're not going to derive for this purposes of this, but it should be pretty obvious for the acceleration time graph, because the formula is a is equal to minus omega squared x. Sorry, a is equal to minus omega squared x. So when will a be at its maximum value? When x is equal to the amplitude, a. The maximum that this equation can produce is a, the amplitude, because cosine and sine have values between 1 and -1. So our amplitude here will be omega squared a in each case. And so let's go back and let's just finish off this example that we were looking at. So for the example we gave was a simple harmonic oscillator with an equation of motion of 3 cosine pi t. So just continuing that same example, we would have v is equal to, so now we would take omega, which is pi, and a, which is 3. I'm going to reverse the order of these, and that would be 3 pi sine of pi times t. So the actual value here, if we were looking along the axis, would be 3 times pi, or a little bit more than 9. And for the acceleration time graph, we would be looking at a is equal to, so we have minus omega squared a, so that is going to be, so a we said was 3, and that's going to be pi squared cosine pi times t. Now for the record, the values that are inside here will probably not be whole multiples of pi. I mean, that would be very unusual. Typically these are going to be numbers. If you remember from our the previous example that we had used before, we found values of, for example, values of omega of 4.1. We found a value of omega here of 2.83. And remember that the period of time, if we were to multiply the period times the angular frequency, when we multiply these two things together, we're going to get a value that's equal to 2 pi. As the equation obviously shows is going to be the case. If we move the w over here, omega times the period is equal to 2 pi. So regardless of the actual values of the numbers, this argument, whenever it reaches a value equal to 2 pi, which is about 6.28, every time it reaches that value, we will have completed one full cycle, whether it be acceleration, velocity, or the displacement time graph.